At an international conference on open and innovative education, Professor Todd Campbell, professor of science education from the Neag School of Education at the University of Connecticut, gives a talk about representing disciplinary activity in STEM education, which finds its importance when considered in the context of situated sociocultural and resource perspectives on learning. Professor Todd focuses on unpacking a theoretical basis for the representation of disciplinary activity in STEM education, while also providing examples of resources and tools useful for taking up these more innovative forms of teaching and learning in classrooms.
Here's presentation outline. So I want to do three things in the talk today. First, I want to provide just a little bit of theoretical grounding for thinking about the changes that have been proposed in the next generation science standards in the U.S. I want to talk about situatedness, sociocultural and resource perspectives on learning, and I want to try to weave those together, and I want to come back to those often as I start talking about what we're trying to accomplish with the next generation science standards, and then I also try to connect that to what's happening around the Common Core State Standards, which is focused on English language arts and mathematics learning. And so I'll try to weave those together. And then the next thing I want to do is kind of reveal what the focus of the next generation standards is, why it's so different, drastically different than what we've done or what typically happens in U.S. classrooms, and just why that might be. And then the last thing I want to do is provide kind of some frameworks that we've been using to, like the national standards are these high-level policy documents that try to orient us to a different way of thinking about instruction. But then we still, as educators who work with students daily in classrooms, have to figure out, like, how do you take that policy, those bigger visions, and make them into something that's palatable and tractable within classrooms with teachers. And so I want to share kind of a framework for how we can work across, like, school districts. We have collaborations across school districts, and we try to work across those school districts in ways that the school districts can learn from each other while we also learn with and from them as well. And then I want to share some of the model-based inquiry work that we're doing, and this gets right down to the level of what might happen in classrooms and how we think about supporting pre-service teachers. I work a lot, that's my main focus at the university, work with pre-service science teachers to try to get them ready to go into class and start really at high levels. And then also thinking about, like, if we're going to work with pre-service teachers and they're going to go into mentor teachers' classrooms, then how do we work with mentor teachers in ways that the pre-service teachers don't experience this two worlds pitfall of us having expectations at the university and there being different expectations on out in local schools. So we try our best to form, we've done some of our work around networked improvement communities, so we try our best to form this systemic initiative that looks across the whole system to try to, like the idea is every system's perfectly designed for the outcomes that it currently gets. And if you're going to try to change something, then you need to think about systemic change. And so for me, that means stepping out of my narrow focus sometimes of just what happens in classrooms to thinking about, like, what presses on classrooms and how can classrooms be better supported to change the instruction that we try to pursue. I want to start with the theoretical. I have three parts I want to talk about, and I don't go into that much depth, but they're important, and I'll try to come back to them. So I'll start out one theoretical perspective I think is important. It's a situatedness or situated perspective, and this just talks about how activity is not neutral, like it happens, and it shapes the learning that happens within. So the environment and the space and the local culture and history of a place, they push and they pull on learning that happens in those spaces. So learning is situated. I'll read some of this early, but then I'll stop doing that. So the activity in which knowledge is developed and deployed is not separable from learning and cognition, nor is it neutral. Rather, it's an integral part of what is learned. Situations might be said to co-produce knowledge through activity. So that means if we want students to get a really great understanding of scientific activity, of what scientists do and why it's so important, how they pick up and develop knowledge pieces, or how they use practices to hone and refine knowledge pieces, then we need to try to situate their experiences within those common kinds of pursuits like scientists might pursue, and give them opportunities to pick up knowledge pieces and use them over time. in practice, knowledge, and that's thinking about like competence as a position, recognize and support individual in disciplinary pursuits, is not the property of individual representations in their head, the cognitive view, but rather a more relational property of individuals in context and in interactions with one another, the situated view. Therefore, knowledge resides somewhere between individuals and the social context in which their work is nested. Here, practice is something that people do as part of a historical, cultural, and local context in community. So this is thinking about the situatedness or situated perspective thinks about, like, there really is learning that's happening inside people's heads, but it's also so connected to the context and the people they're interacting with. So the implications from this are knowledge cannot be fully understood without additional contextual information, since knowledge is connected to the motivation from which it was developed, as it is to the tools and subjects which produced it. So context, problems, spaces, and pursuits matter. So this is coming out of activity, a little bit out of activity theory. The subject-object dialectic is what drives activity. So we want to think about, traditionally in the U.S., there's differences, but really traditionally and historically, learning in science has meant, especially at universities, sitting in large lecture halls and listening to lectures and trying to understand these things a little bit independently. And that might get us close to the content knowledge, but it doesn't get us close to how that content knowledge might be really useful in authentic pursuits. And we're not potentially giving students chances to be scaffolded and supported to pick up those ideas by some learned other who might be able to help them do that. Sociocultural perspective, this isn't as long. This idea thinks about learning is social and a cultural process. People bring their resources to their learning experiences, and we should do our best to try to tap those resources. We are social. Knowledge is a matter of competence and respected, valued enterprises. Knowing is a matter of participating in pursuits of such enterprises. So ultimately, I think what we want to try to accomplish in STEM education is positioning citizens, people who might pursue STEM, but also just citizens, positioning them in ways that they feel like they could participate in, maybe not STEM as a professional practice, but STEM as a thing that influences our lives that we need to make claims about. So like in the U.S., climate change is a really important topic that we need to think about right now, and we need citizens who are really ready to jump in and participate in the discourse that's happening around that, and we need to make sure that we prepare them to do that by positioning them in real-world pursuits like what climate change presents. So here, the implications are learning is participation. Laven-Wenger communities of practice talk about what we really do in human activity is try to accomplish things. And so learning is the ability to pick up things that are helpful to us to accomplish things. And I'll share a little bit more about what those might be. The last theoretical part I want to talk about before I jump into some more concrete ideas is the resource perspective of cognition. And this is really, I think, helpful for orienting to the way I'll talk about the instruction that's been kind of, not instruction, but the vision for science teaching and learning that's outlined in the Next Generation Science Standards. So the resource perspective talks about, this is DeSasa, and one of his students, David Hammer, is at Tufts University, talks about knowledge being organized in fine-grained understanding. So knowledge are fine-grained pieces that we pick up and activate when we think they'll be useful, and we try to connect them to other little pieces to build an explanatory account of what we think we're seeing. So what we do when we experience this situation, we're trying to understand something or explain it, is we activate a knowledge piece, or we activate multiple knowledge pieces. And then we try to latch them together, and sometimes we unlatch one idea and get rid of it because it's just not applicable right now. Or sometimes we take an idea that we think we understand, and we start talking to someone else, and we figure out they understand it differently than we do, and maybe I like the way that their understanding seems more logical, so I'll try to think about whether I need to change how I think about a particular idea. So the implication of this, I think down here, is we can think about learning as kind of the refinement of everyday thinking, and that's different than a lot of times, I think, historically, how we thought about learning. We thought about learning as people don't really understand things, and we need to give them these really powerful explanatory tools of science or STEM, and that'll help them. So we need to get rid of what they know and bring in what those really validated scientific ideas. And that's kind of the opposite of this. It's saying people's ideas and experiences are valuable, and if we can help connect their ideas from their everyday lives to disciplinary ideas, then that would be a stronger foundation for understanding something. So I want to give you an example here. I don't know how well I'll do with it. There's a video from about 25 years ago called The Private Universe. It's pretty popular in the US. What it did 20 years ago is it tried to show how we're really failing our education. Our education system in the US was really failing. So what it said is they took a middle school learner. Her name was Heather. They videoed and they showed where she had just completed instruction with her science teacher. They had just finished a unit exam, and Heather was like a top student. She had made hundreds. She definitely knew what was going on. It was about the seasons. And so she had been able to finish the fill-in-the-blank exams and all the assessments the teacher wanted. So when they asked the teacher to share one student that they thought really had a good grasp of what seasons, how to explain seasons, they picked Heather. So they took Heather in a room and they asked her to explain it. And what I think at the time they were trying to show was that students have misconceptions. And I want to argue it a little bit differently, and I want to use this to try to argue that. So what Heather did is they said, Heather, how do you explain the seasons? Like, why is it hot in the summer and colder in the winter? And so Heather stopped for a minute, and she said, oh, that's simple. Well, you see, the earth revolves around the sun, right? And she gave us the number of days. And it takes this long, and the Earth's orbit around the sun, it's an ellipse, right? So that means sometimes it's closer and sometimes it's farther away. And then, because it's closer and farther away, when the Earth gets closer to the sun, that's when you have summer, and when it's cooler, or when it's farther away, that's when you have winter. And so that was lifted up 20 years, and it's pervasive in our like pre-service teacher education. That's misconceptions, and we got to work on those misconceptions. We got to stamp them out, and we got to change them. I would argue differently, and I think these researchers would too, and say what Heather might have done is picked up really useful knowledge pieces from her everyday experiences and from some of the things she learned in science class, and she tried her best to put them together when she was put on the spot to do that. And so I would argue like Heather may have in her everyday experiences walked up to a hot stove or a fire and noticed when she got close to it, it was hot. And when she walked away from it, it was cooler. And then she noticed that the earth had this elliptical shape that it went around the sun. And so she just put those two ideas together and explained that's the reason for the seasons. And so while that's not exactly the scientifically, it's not accepted position on why we have the seasons or the explanation, what it is like it's using accurate, not misconceptions, but it's using accurate evidence and ideas from everyday life to try to connect pieces to explain something. And so this resource perspective is really nice because what we can do is if we get students' ideas out there early, that's really important because that's how they're really thinking, whether we acknowledge it or not in our instruction, which is what happened in that classroom. We can position them to think about those ideas continuously. We can give them activities and investigations that they can engage in so that they might over time question some of the ideas that they proposed. And we give them the space and safety in our classrooms to change those explanations and to celebrate like that those changes are happening and to work with others in this kind of pro-social behavior to work toward we're just working toward trying to figure this out. I think I'll try to pull all these together and say what I was trying to do with these theoretical perspectives is try to say the underlying part, the true nature and power of science ideas. I'll add on to that science practices. So the true nature of science ideas and science practices, they're not really understood until they're used in some authentic context where there's some level of uncertainty and they're able to know something with those ideas. So that would mean like levels of uncertainty would mean like I would argue you're not really engaging in a scientific practice if you're not trying to figure something out. Like it might look like it, but if there's not that level of uncertainty and you already know something and you're just trying to show somebody that you know something, I'm not sure that's a scientific practice. And so a scientific practice, to really get a grasp of what a scientific practice is, it would be necessary to position students in ways that they were in an uncertain where they didn't understand something and they needed to pick up a practice to try to make a knowledge claim, and this helped them to make that knowledge claim. So that the argument is that we need to try to position students in ways that are similar to how scientists or STEM professionals are positioned, so that they get a sense of not only the what are important, like the disciplinary ideas, but also the how, why, and when they're important. And so they get a chance and facility to pick them up in useful ways as they move forward. The last one, I'm trying to pull it together. Again, I'm using Bransford as a really good piece. Understanding how productive ideas are, like the mechanistic accounts of matter or the particular nature of matter. And I'll even add on there like modeling, like argument, like explanation, those practices. They may not fully be within the reach of learners until the idea is used in an authentic context where uncertainty is there and is recognized that the idea, the practice, can account for something that wasn't accounted for previously. So that's the kind of like learning environment I think we want to try to create in our classrooms, which is a monster challenge, especially like in the US. That's not what happens in most classrooms. It leads me to now I get to like what is this dramatic shift in instruction we're trying to pursue in classrooms in the US. So down here, Brian Reiser is one of the writers for the Next Generation Science Standards. He's at Northwestern University, and he talks about this vision in the new standards document. It's dramatically different than what happens in most US classrooms. And we also know this because we do national surveys of our science and mathematics classrooms across the US. They do them about every 5 years. We just had one come out in 2018, or I'm sorry, right at the beginning of 2019. So it gives us a sense, or surveys of 50,000 teachers, and it gives us a sense of what's happening in their classrooms. And we know from national surveys what really happens in US classrooms. I don't know how you perceive US classrooms, but I can say what those surveys tell us about the classrooms is they might be a little bit progressive in that we do a lot of activities. We do a lot of activities to try to share an idea or share an idea with students. We do a lot of activities connected to an idea, but we don't do a good job of pressing students to develop explanations of things. And we don't do a good job of creating coherent learning experiences where one idea is connected and experience is connected to another one. And so that's the thing I think we need to change that is dramatically different and possibly what Brian Reiser was talking about there. So now I'll get to what are the dramatic shifts of teaching and learning envisioned in the framework in the NGSS. And I would venture to say, based on the theoretical ideas that I shared, these might extend beyond just science education. And I know like meaning making is really emphasized in the Common Core state standards in the US. So they're even taking this up in mathematics and English language arts to say we need to position learners in opportunities to try to understand something that they previously didn't understand. So I love this quote. This was offered by Michael Ford. He's at NSF now, but he was at the University of Pittsburgh in 2008. Like, this is a great article. He said he looked at science studies scholarship, and he made this really bold claim, and then I saw everybody citing it, and it made so much sense. I know you can push back on this. There's so much nuance underneath it, but this gives me a little bit of a perspective of what we might be trying to accomplish in STEM classrooms or science classrooms. So science is essentially the construction and critique of explanations about events that happen in the world. He says that's what we try to do when we engage in science. There's lots of nuance there and lots of technicality, but I'm not getting there. But if that's what it is, then why don't we, if we want students to really have a grasp of the how, what, when, and why, then why don't we try to create spaces where they're constructing and critiquing explanations about events that happen in the world? So that's what the NGSS, Next Generation Science Standards, has tried to do. They proposed this vision of three-dimensional learning, and I'll go into that in more detail. But three-dimensional learning, it's been defined by Reiser, I think, in Krychek. Joe Krychek was another writer from Michigan State University. Three-dimensional learning is engaging students in science and engineering practices. That's one dimension. To use disciplinary core ideas, that's 2 dimensions. And cross-cutting concepts, that's the 3rd dimension. And this is a really important part, which I'd argue is the most important shift in the standards, among other things that are important too, to explain phenomenon or solve problems. Like, that's the object of activity, to explain phenomenon or solve problems. That's what typically has not happened in US classrooms. Like, we haven't positioned students within the activity that would give them chances to develop facility with the use of ideas and understandings of the ideas and facility with the practices. So we engage students, we're trying our best, which is a massive lift. We're trying our best to engage students in figuring out instead of just learning about decontextualized knowledge. And that's what we've done historically. So what this means, I want to share like a little bit more about the 3 dimensions, and then I'll try to share what the implications of this are for classrooms. So this would be the science and engineering practices. Science studies reveal how practices emerge out of problems scientists have with knowing. So he's arguing that these practices are just these things over time that develop because we didn't know, and we need ways to show people that we know something if we know it, or that we need ways to contest what we think is happening, and that would be like scientific investigations. And then down here, Ford, working from the philosophy of science, Rouse's work, talks about performance, or practices are really just regularities of performances that have over time been shown to be useful for working at knowing or making stronger knowledge claims. So we're arguing that these are the practices in NGSS. They're the starting point, and they're not localized yet, and they can be. But things like developing and using models, constructing explanations, engaging in argument from evidence, those are the practices. There are 8 practices that we want students to gain facility with because we think that will help them work at knowing. And you can see here, I love the way this is represented. They're not represented like this in the framework. It's represented like this because it isn't a hierarchy, and we don't step through this like a scientific method, and there's some recursive activity happening there. Like I'm in a context-specific situation. I'm trying to help my students understand something. I'm trying to position them in some level of uncertainty. And for this particular context, these practices might be the most useful ones. And they might bounce back and forth across these because they're necessary to get. So I might engage in argument from evidence when I'm initially trying to explain something. And then I might engage in investigations because I want to test some idea that will help give me some evidence. And then I need to argue about that evidence again. And I'm going to take that evidence and build an explanation. So those are like the ways these practices can be used as this repertoire to come together and try to help make claims or refute claims. Here's the second dimension, cross-cutting concepts. So examples of these are cause and effect, stability and change, energy and matter, patterns. There's 7 of these. CCCs provide students with connections and intellectual tools that are related cross-disciplinaries or discipline areas of disciplinary content. So we're talking in the next generation science standards with life science, earth and space science, physical science, and then engineering. So these are the ones that we've argued are applicable or useful across disciplinary context. And then I'll go here. This could be ways of oriented to uncertainty in constructing explanations or solving problems. So for me, I try to think about this as I came upon something I saw the other day, and I really didn't understand it. I didn't know how to think about it. I have some ideas I'm ready to try to lift up or activate, but I'm also just kind of struggling with how to think about it. So one thing I can do is look at these cross-cutting concepts and say, I think there's something going on with how energy is being transferred in what I'm observing, that real thing that I don't know how to explain. So let me try to think about how the energy is being transferred and how the matter that thing is made of, those things are made of. I should give you a concrete example that help how those things that might be important. Or if I think about trees and natural selection, let me think about patterns I might observe. And are those patterns ways that I can organize my thinking that might give me some leverage to really begin to get an explanation of what I see that I'm struggling to understand? So the first ones are practices, ways of working at knowing. I think these are more comparable to like disciplinary ideas, but they're not there because these are the ones that stretch across disciplines. And then the last one is disciplinary core ideas, and I think these are the ones we always, they're no less important now, but they're only important in context connected to those other dimensions. So ways that they try to decide what happened here. So what we wanted to do was try to narrow down to some really explanatory, powerful ideas in each discipline and let some of it go. So if you look at a biology textbook, you know that it's stacked with ideas and nuances. In the next generation science standards, we wanted to make sure that we picked up the most powerful explanatory ideas, and we thought about the ways that students could learn them across K through 12. So they have broad importance across multiple science and engineering disciplines. As a key organizing concept, they provide a key tool for understanding and investigating more complex ideas and solving problems. This is important. They relate to the interests and lives of students and can be connected to societal or personal concerns that require technical knowledge, and they're teachable and learnable over multiple grades at increasing levels of depth and sophistication. So what's nice that they've done in the next generation science standards, and it's just like I'm lifting it up like I've been drinking the Kool-Aid, but it is our next humble attempt to draw on the research that we've done over the last 20 years since we had our last standards documents, to try to say this is where we think we're at right now. And we know in 20 more years there's going to be a refined way to build on what we know now because of our 20 years of experience doing this work. So what's nice about these is they drew on learning progressions. You can critique learning progressions. I think we've done that a little bit in our literature. A learning progression is just how students might start at early grades to think about a disciplinary core idea like maybe evolution, or natural selection. They might think about the difference between living and non-living in K through 2, and grades 3 through 4. They might start thinking about why offspring look a little bit different but similar to their parents. And in grades 5 through 6, as they keep moving up, they might continually start thinking about how environments seem to be able to provide the resources, I said that opposite, resources that organisms need. So there's this progression that we can use to provide foundations for students to learn more sophisticated ways about ideas across time. They've also done this for the disciplinary, or the science and engineering practices, and the cross-cutting concepts. So they said, what would modeling look like for third graders? And how would that be more sophisticated for middle schoolers? And how would it be a little bit more sophisticated for high schoolers? So like in high school, it might have a lot more computational. It might be a lot more about computational thinking and computational modeling, whereas it might not be that in middle school. I'll summarize what I tried to share about the next generation science standards. The three-dimensional learning for the purpose of sense making through explaining phenomenon or solving problems, that's the biggest shift that we're trying to get at. And it's monumental. Like, it's no small task because education moves slowly. And we've already created a system that works for the education that we've traditionally gotten. And I would argue that's representing scientific activity. And so we're shifting from learning about the contextualized ideas and practices. It's not time to learn about the scientific method at the beginning of the academic year. It's time to, across the whole year, learn about how practices are useful for refining knowledge claims across time. So one way to do this is, this came out in just recently, 2019. It's a great article by Ko and Chris. It's in Science Education. It's a framework and resources for engaging students in representation of scientific activity in classrooms. So they said in this article that this is broadly accepted as the epistemic criteria that needs to be included in the experiences students would have if they're going to be learning in a setting that we would say was a next generation science design setting. And so one thing that it would need to have is a driving or anchoring phenomenon that sets the goal or the problem space for instruction. So we need to have a reason for what we're doing. And that needs to be, students need to think what we're doing in this setting is we're just trying to explain that thing. And the reason we're engaging in this lab 3 days from now is because that's going to give us some more ideas that we might bring to this thing to help explain it. The next one is you need some central model or explanatory account that's incrementally revised over time to explain the problem space. So we use modeling a lot, and my modeling is that word is different and described differently across disciplines, but I would say it's sets of ideas for explaining something that happens in the world, and we use pictorial representations with text. And so we would use a model, an initial model, and we would have students think with that and show it to us, and then we'd have them come back and refine that over time. So at the end of the unit, they would work with a group, and they would have a more sophisticated explanation of the problem space at the end. You can also do that with the argumentation. The next one is the purposeful use of investigation, and this is broadly construed, so it could be random controlled trials, but it could just be I'm going to try something out and do a qualitative kind of observation of whether what I thought would happen happened, and then I'm going to argue from what I saw happening. So those need to be part of the sense-making process. students need to have opportunities within a unit to do some investigations so that they can get a sense of if how they're thinking about something is actually happening over time. And then the last one, this gets back to the sociocultural perspective of, and the use of discourse, evidence, and argumentation to generate claims and support evidence to build and refine aspects of the explanatory account across time. So there, we'd focus on, and we've been really intent early on in the implementation of the next generation science standards of trying to find some talk moves that will help support us to change environment so that discourse is coming from the students, but in a coordinated way that helps over time develop a more incrementally sophisticated model or argument over time. This is really powerful. I've used this with, we have a multi-district collaborative of 5 districts around UConn who also host our pre-service teachers. We struggled because there are 5 different disciplines and we have local control in the US, and so districts can make their own local decisions. So when they're asked, even though at a state level when we adopt the next generation science standards, when they're asked to implement it, then they can pick up whatever strategies they want to do and try it out. So it's really hard to collaborate across districts when everybody's doing different things. And so in our district work, we came to this and we revised and negotiated and changed them slightly, but if we come to this kind of agreement, then we can start working together because we can say, how do we identify anchoring phenomenon in ways that are powerful enough and engaging enough to have students pursue something over a longer period of time. So we could develop practices, tools, and resources that can travel across districts because we have some common commitments. And then this jumps into, like, now I'm getting really specific, like what do you do in classrooms? So we do model-based inquiry is instructional way of planning an instructional unit. So what typically happens in a unit traditionally would be, I want my students to be active, so I'll create a lot of activities, it'll put ideas on the table, and then I'll give them a summative assessment at the end to see if they learned it. And so this is trying to shift gears and say, we want an initial explanation, we want their ideas on the table, we want their idiosyncratic ways of thinking about the world there, and we want them to refine those ideas over time, refining everyday thinking. We also want to use discourse, we want to keep track of ideas and make public records, and we want to keep revising those ideas and public records across time. So we're trying to shift instruction, and the way to do that, I'll keep going. We try to come up with, and this is based heavily on ambitious science teaching. This is work out of the University of Washington, Mark Winchell, Jessica Thompson, Melissa Broughton. Amazing work and website, Ambitious Science Teaching. If you, ambitiousscienceteaching.org, went to that, it's amazing. We're building ours. This is our way of kind of localizing the work that they've done for the curriculum work we're doing with teachers. So we say, we start out, these are the high leverage practices we would want to engage pre-service teachers in. So if we could teach them some high leverage practices early, they can get a really running fast start in classrooms. And if their mentoring teachers had similar experiences with similar practices, they could work together and it wouldn't be a disjointed experience for the pre-service teachers learning to teach. So ours are eliciting ideas about phenomenon. I can go into these because they're in slides. The first high leverage practice is you do a lot of planning ahead of time, but then after the planning's done and it's time to work with students, you elicit their initial ideas about phenomenon. So introduce it, get them to develop their initial ideas. There's a lot of nuance even beyond that, but that's a start. And then from that, you can see that was it. It went to here, negotiating ideas and evidence through tasks. So once we get their initial ideas and some initial models, then we've strategically thought about what ideas are important to try to put on the table for students to reason about, so that we will engage them in some tasks that they can use to refine their models, their initial models, to come up with that more sophisticated explanation. And then down here, we would build some consent. So we would take what we learned across those tasks and we would take them back to our model and we would refine them using the ideas that we learned about. And then it gets to the last one. And then we'd establish the credibility of the models. And then we also do a little bit of transition here. So we would create some criteria in that building consensus that we think needs to be present in these final evidence-based explanations we're going to ask students create. But in that building consensus practice, we would do that at a group level. So we would go back and renegotiate what their models look like in groups. We also want to see what individual learners know. So we want to push them toward an individual evidence-based explanation. So we want them to move from that group resource that they have now as a model and some other public records that we've created for them as a class that they can access. And then we want to ask each individual student to write an evidence-based explanation that would explain the imploding tanker car or whatever the phenomena is that we've been looking at. Here's a representation of that Finegrain Resources perspective, where you can see student ideas, you can see some disciplinary ideas, cross-cutting concepts coming in, you can see some student ideas moving out, and in the end you can see a more sophisticated explanation at the end. And down here I've tried to lay that across the framework we use for designing curriculum. So here's some examples. We have a website with some curriculum we've developed, and so here's a set of twins that don't look alike, but they're twins. So the question is, how do these twins come from the same parents? And then over here, some more life science examples. We have more here, like there's a crazy case, down here, the blue people of Kentucky. There was a group of people that lived in the backwoods of Kentucky. I don't mean to sound derogatory toward Kentuckians, but they had this genetic disease that caused their skin to be blue. And so the question is, like, what's going on with these people, and is it just magic? But it turns out it's science and it's genetic. And so this unit is situated around trying to explain that. And then there's a beetles issue with beetles associated with climate change. So I'll stop there.